Welcome to tonight's event. I'm very glad that you're all here. We have a very interesting guest today. I will introduce him in a minute. First, I want to thank Base for giving us this beautiful space, and Binary District for organizing the event, and the Blockchain Research Institute for supporting it. For those people who don't know the Blockchain Research Institute, it's an international research and development center focused on facilitating the production and implementation of blockchain-based solutions. For those who don't know me, my name is Rico Grimm. I am the co-founder and editor-in-chief of a German language online magazine, which is called Crowd Reporter. And I know a thing or two about decentralization because we are solely financed by our readers. We call them members. We are structured as a cooperative. We started with a very big crowdfunding, and we try to cooperate with our readers as much as possible while writing and researching articles. So, and last year my readers asked me, or they asked us, guys, what is this Bitcoin? We explained it to them, and this is how I got into this space. But today we talk about something. We talk about the one thing that seems to be the biggest topic right now in the cryptocurrency space, and that is scalability. I don't know who of you was here for the last two events. We had Joshua Lind presenting a new state channel solution, and we had in the last event a new cross-chain transfer solution. And both of them were very distinct. You know, maybe they could be connected, maybe not. Maybe they could supplement each other, maybe not. And our guest today, Bryan, will introduce another idea, another concept to actually solve the scalability crisis or the scalability problem. Bryan is the head of the Decentralized Distributed Systems Lab at the Swiss Federal Institute of Technology in Lausanne. I'm very glad that I read that correctly. He earned his PhD at MIT. He was born in the US, grew up in California. And I don't want to go into too many details of the concept because Bryan can do that better, obviously. But broadly speaking, ByzCoin wants to create a consensus group that works collectively on blocks with the help of mining. And only 2/3 of these miners have to approve any given transaction, and so you can make transactions faster. The name ByzCoin comes from a novel Byzantine consensus protocol it uses. Before I hand over the mic to Bryan, I just want to give two thoughts. Actually, when I was preparing for this today, I was just thinking about how many different solutions, concepts, and ideas are out there, and they all want to tackle the scalability problem. And you could say, oh gosh, yet another scalability solution, you know? I mean, everybody wants to solve it. It seems to be like the holy grail right now. But I don't think that cynicism is a very good response to that. Actually, we should all be very thankful for that, because out of these hundreds, maybe thousands solutions, 1, 2, maybe 5 or 12 will be the ones that we will actually use in 10 years' time, maybe. And we don't know yet which of these ideas that we talk about today are the ones that will be used in future. So we should pay attention to what is happening right now. And if this is not convincing to you, then I want to give you just a small analogy. Around 550 million years ago, Earth saw something that never ever happened before and never happened after. It was called the Cambrian explosion. And as life as we see it today, developed at this time in a very short span of time, 5 to 10 million years. That's just merely a second for Earth. All the basic concepts developed. I mean, can you imagine that before that, organisms were not symmetric? So the concept of a right side looking like similar to the left side was not invented yet. So it didn't get introduced to Earth. And there are even more concepts. And I think right now in the cryptocurrency space, we can see something like the Cambrian explosion happening. You have many, many concepts, and some of these will actually survive and will be the backbone of the future development. But, and this is just my closing remark, I think we do have another problem, I would say, and that is how to, the question of social scalability, and I don't mean it in the sense of Nick Szabo, but in another sense, but how to socially scale a technology, especially when it's decentralized. So I don't know, so how do you introduce it to the people? How do you help the people to use it? I don't have an answer for that, but I do know that biology this time cannot give us an answer, because in biology it's just, if you find your niche, you survive. If you don't, you die. And I don't think that this works in a human-centered technological space. So nevertheless, one part of the solution, or one part of the answer to this question I just asked, is definitely to listen to many different concepts, to listen to many different ideas, and maybe some of you in the audience tonight picks up Bryan Ford's research, takes it to onto another path, develops it further, integrates it into his own project, and something big come out of it, out of this little event. You never know. And this is why we should listen very closely to Bryan now. And yeah, good to have you here.
Yeah, thanks so much for the introduction. And it's great to be here. Yes, so I'm a researcher at head of the Distributed Decentralized Systems Lab at EPFL. And for the past for many years, I've been working on building decentralized systems using applied cryptography in various ways. I've worked on anonymity and many other systems, but for the past 3 years mainly, my lab has been heavily working in the area of blockchains and trying to figure out how to build the next generation of more scalable, faster, more consistent blockchain. So, but before I get into that, I want to just kind of introduce my lab and set the big picture. So we all know today's information systems are generally horrifically insecure, that we're getting data breach notifications all the time. From different companies everywhere. And in part, this is because our systems are global network systems, and our computing infrastructure is becoming extremely complex. And it was designed in what I call the single, a weakest link security model, where it typically takes an attacker to break just one element of security of a system, compromise one account or whatnot to create a major compromise. And as our systems get bigger and more complex, they scale to weaker. They become weaker rather than stronger, right? So addressing that problem and fixing that problem is really the central focus of my lab. I see this as a grand challenge. This is very closely related to blockchain, but not specifically blockchain. So I don't only do blockchain research, but our broad goal is to figure out concepts to make systems, to turn around this weakest link security model and create a strongest link security model, where an attacker would always have to break multiple links in order to get anywhere, right? And so that's just a loose analogy, but it's a good place to start, I think. And ultimately, we want to not only get to a strongest link security model, but we want to scale that. We want systems to scale such that their security scales with their performance and capacity, so that as we build a bigger system, it gets more secure rather than less secure as current systems do. And this is where, to me, blockchain is so exciting, and I'll get to that in a minute. So just to introduce my lab, who did all the hard work I'm taking credit for, as academics tend to do, but I want to acknowledge them from the start. But so with that brief introduction of my lab in mind, of course, you wanted to hear about blockchain and what we're doing with blockchain and systems like Bitcoin. So I'll get to that. So, Bitcoin and blockchain is incredibly popular, and I'm excited about this because 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 Bitcoin basically finally brought this idea that it's both possible, practical, and extremely compelling to bring this strongest link security model out of computer science, arcane computer science literature, and really deploy it, right? And so most of the concepts behind Bitcoin were not really new, but it was a super novel, interesting system putting together these different concepts such as proof of work and distributed ledgers and things like that. And of course, it was basically the first successful cryptocurrency. I won't talk a lot about it, since I assume all of those who are here, you're here because you're already interested in this and know a lot about it. But just to refresh the most basic concepts, of course, the basic idea of Bitcoin was to create an alternative currency that's information based. It's not based on the value of physical things, but based on basically a record, a common record of who owns what virtual currency called Bitcoin, right? And in some sense, banks have been doing this for centuries, right? You know, keeping ledgers of who owns what or who owes what to who. But Bitcoin wanted a more decentralized version of the ledger-based abstraction, and so Bitcoin created this, proposed this notion of a blockchain-based ledger, a ledger that everybody keeps a copy of. So many different people, anyway, anyone who wants to can keep a copy of, and they work together to keep each other honest, right? And you know, I'm sure you're all familiar with, in general, what the Bitcoin blockchain looks like. You know, a series of blocks, each containing a bunch of transactions that the miners produce periodically. And of course, this is not, even though it started out as a cryptocurrency, there's tremendous interest across many sectors of industry in the underlying ledger concept and the way it can be applied in many different industries. Okay, so you know, that's all the high-level background and stage setting I wanted to start with. So the problem that I see is that so you know, it's a super exciting and interesting concept, but the currently deployed blockchain systems, including Bitcoin, have a lot of limitations, especially performance and scalability limitations, which I'll be focusing on in this talk. Many also have security issues and consistency issues and stuff like that. But I'll mostly focus on scalability here. And so what do we want to try to do? My group's goal is, at least in the blockchain space, is try to figure out what are the tools and concepts we need to build truly scalable blockchains in a modular and flexible way. What are the tools that we need to put together to build blockchains that are fast, that can commit transactions in seconds rather than minutes or tens of minutes? Blockchains that can keep private data private, that remain strongly available, etc. So with that in mind, I want to talk about several particular tools and ideas that we've come up, that we've been developing in the DDIS lab, that all sort of fit together, and they fit together to create scalable blockchains, especially. And so I hope. I hope I'll be able to convey, you know, the reasons, both, you know, at a high level, why these protocols are needed and how they fit together, and also, you know, give you some tools to work with and think about in the future. So of course, there's I'll get into some of the some level of technical detail. I'm not sure how technical you are generally, so I'll get into some level of detail. But of course, I can't get into everything. There's a lot I'll have to leave out. And so there are papers. If you want more detail, we can discuss afterwards. There's also papers that I'll point to, and we're happy to talk and help people who want to use these ideas and protocols as well. So first, I'll talk about ByzCoin, the basis for our scalability work. And the sub-problems and sub-protocols it uses of scalable selective signing and bidirectional verifiable blockchains that we call skip chains. And then, if I have time, I'll also give you a brief overview of OmniLedger, which builds further on ByzCoin to provide further scalability. Okay. So let's dive right into ByzCoin. So any blockchain requires consensus. So it's easy to have to replicate a ledger. If the ledger just never needs to change, then just give everybody a copy, and everybody can verify the consistency just by checking a hash or something like that. The challenge always comes from the need for consensus, for everybody to agree on how and when the ledger changes, how and when we add a new block, right? And Bitcoin introduced this idea that has become known as Nakamoto consensus, a very novel, interesting consensus algorithm that's very probabilistic, and I'd like to describe it as a crypto lottery. Basically, a bunch of miners constantly printing their own lottery tickets by feeding random numbers into seeding their blocks with counters, and using hash functions to compute pseudo-random numbers and see if they get a winning ticket. And so miners have to do this, billions or trillions of times these days to get a winning ticket. And then when they do, they get to add one block worth of transactions to the blockchain, and this comes with a reward as well. Now, I'm not going to get much into how all these transactions work. I assume many of you are already familiar with that, and that the transaction and coin transfer is not the focus of this talk, since that's fairly orthogonal to the scalability. But I just want to look at the key properties of Nakamoto consensus. First of all, it's only probabilistic consensus, so it can produce two histories, at least temporarily. Namely, two miners might either accidentally or maliciously produce two blocks at about the same time that try to compete. And Bitcoin says, okay, chill, don't worry about this. It's not the end of the world. Let's let that happen. So this is from my perspective, one of the very innovative things about Bitcoin. It's very chill. It says, traditional consensus protocols would not accept even temporary forks like this, but Bitcoin says, okay, let's allow the fork to happen for a while, but some miners will be working on one version of history, and other miners will be working on other versions of history, and then at some point, one of them is going to successfully add another block with more proof of work, mining power attached to that, hash power. And then when that happens, everybody is going to gravitate to the longest, or more precisely, the chain with the most hash power, the most work embedded in it. And then that resolves the fork, right? And probabilistically, well, the fork could survive 2 or 3 times, but it gets exponentially less likely with each block that any fork survives under normal circumstances. So this probabilistic consensus protocol was very interesting and attractive for its simplicity from a computer science perspective, but it has also has these problematic issues. First of all, that these blocks actually don't happen very often, and they can't this protocol really has to be tuned so that miners don't create blocks too often, because if they're created often enough that they don't get a chance to propagate through the network before the next block happens, all kinds of bad things happen, both in terms of performance and security. And there's a lot of other good research that analyzes and explores, well, how far can you push Nakamoto consensus before it falls apart? But it does fall apart if you try to speed it up too much. And so you have to run it fairly slow, and you really only get weak consistency. If you just wait for one block commitment, you're not really certain that you receive the payment or your transaction will be stable unless you wait for several blocks. Satoshi Nakamoto recommended 6, but there's nothing magic about that, right? So this presents the big scaling challenge. How do we make it, blockchains like Bitcoin scale, not just by tweaking the parameters so that they run a little faster, but can we scale them by orders of magnitude so they can handle orders of magnitude higher throughputs and increased speed? So, of course, there's a huge variety of approaches, and I agree with your introduction that this is a good thing. It's a good thing for many people to be exploring different approaches. And there's a lot of approaches that kind of take the current blockchain as a given and try to add things either on top, like as a second layer, or tweaking the parameters, or simplifying some of the assumptions, like closing the group, or things like that, that are also all reasonable from some perspectives, depending on what problem you're trying to achieve. But at least from my perspective, I feel like there's if we focus on just tweaking the existing structure, we generally only get small improvements, or we lose something that we really want in the process. So my goal has really been to try to say, let's rethink what we need to, add some complexity if we need to, redesign to really get orders of magnitude more scalability. So that's what we're trying to do in ByzCoin. And just to summarize the basic properties, what ByzCoin does is it rethinks the design of a Bitcoin-like blockchain. It is definitely inspired by Bitcoin, but it's redesigned to use consensus groups, which I'll introduce in a minute, to achieve immediate permanent transaction commitment. So when it says a transaction is committed, as long as the security is not completely broken, it will stay committed, and you'll never have forks rolling back transactions or split worlds. It also greatly increases the throughput, because you can run these consensus processes at a much faster rate. And this is because we don't have to wait for 10-minute or even 2-minute or 10-second fixed intervals before we can run the next consensus round. And it also has other useful properties that I won't really focus on. So how do we do this? Well, the most important idea is we have to dig back in computer science literature, all the stuff that a lot of people is often very difficult to read, but it's all often very important as well. Dig back to the classic Byzantine consensus algorithms that existed long before Bitcoin came out. Probably the most well-known one, and the one that we build on, is called PBFT, Practical Byzantine Fault Tolerance, from my colleagues Castro and Liskov at MIT. Without getting too much into how that works, the basic idea of PBFT is it assumes you have a well-defined consensus group, some well-defined set of nodes that's collaborating to commit transactions, or new blocks, or anything you want them to agree on. And to do that, they're going to follow this 3-phase protocol. And again, I won't get too much into the details, but just intuitively, if you're not familiar with Byzantine consensus, intuitively what happens is that at any given time, one of these nodes is typically the leader. It's not trusted, but its responsibility is to propose new transactions or announce that, hey, let's all commit this new block or something like that. There's a bunch of leader election stuff that I won't get into. But then, so the leader announces a new transaction, then everybody has to communicate with everybody else in kind of an all-to-all pattern to convince everybody else that there's a big enough threshold, namely 2/3 for very fundamental reasons. Everybody has to convince everybody else that this proposed transaction is safe to commit. And safe means it doesn't violate any history. It's not inconsistent with, it's not a fork. It's not inconsistent with something that has already been committed. And so that's, at least intuitively, the purpose of the prepare phase, where everybody is convincing everybody else that this proposed thing, whatever it is not inconsistent with history. It can be committed without violating a fundamental principle of consensus. But then there's this third phase called commit, which is needed because even if everybody's convinced that it's safe to commit this, that's not enough to ensure that a sufficient number of nodes will actually remember that it was committed. So just again, intuitively, this third phase, the commit phase, is another all-to-all sign-off process where everybody talks to everybody else and says, hey, are you committing this? Are you committing this? And so on, and make sure that at least 2/3 of the nodes are saying, yes, I have verified that it's safe, and I promise to remember that. And so that gives us the permanence property, the fact that all of the nodes are, or 2/3 of the nodes are saying, yes, I promise to remember and ensure, and in the future ensure that nothing, that I don't let anything get committed that's inconsistent with this history that I've promised to remember. So that's a super high level intuitive summary of the core of the way PBFT works. I hope that makes some sense. Again, read the paper if you haven't. But so it was a groundbreaking protocol. It's not simple. It's quite complex, and people are still struggling to get it right all over the place. So there's you could really say that Nakamoto consensus I think is probably quite a bit simpler than PBFT. So this protocol has some costs to it, certainly, but when you do get it work right, it has very nice properties. Now, it also, in the context of Bitcoin, it has some serious problems, right? And these are the two main reasons that it's not easy to use PBFT in a system like Bitcoin. First of all, I mentioned it assumes that there's a well-defined closed group of nodes that are doing this consensus, and that 2/3 majority thing, all of the threshold logic is based on nodes in that group, right? Now, Bitcoin doesn't have a closed group. It has an open group. Anybody can come and be a miner, and you're supposed to get, you're supposed to get basically mining stake and rewards and stuff in proportion to how many of these crypto lotteries you win, right? So that's an immediate major mismatch with PBFT's assumption. The other mismatch is that traditional PBFT algorithms and systems always assumed that this consensus group would be super small. In fact, mostly it was assumed that that consensus group would be of size 4. Well, why 4? Because that's the theoretical minimum size that a PBFT group can be for their. So some of you have probably heard of the 3f + 1 principle. If there's for very fundamental reasons, in general consensus, Byzantine consensus, if you want to tolerate F Byzantine failures, you have to have 3F+1 nodes total, which means the minimum size group you can have is 4, right? So most PBFT systems were built assuming that would be a very small group, but then Bitcoin comes along and we need massive groups participating in consensus, thousands, if not tens of thousands of nodes, right? And PBFT normally does not, it scales to tens, hundreds maybe with some difficulty, thousands not usually, right? So let's look at those two problems in succession. So first, and how ByzCoin, our design, deals with them. So the first thing we did is we basically we kept Bitcoin's mining idea, but we repurpose it. We say, okay, we're going to use mining and allow these miners to produce these cryptographic lotteries, but they're not going to, when they win a mining a proof of work, that's not going to be associated with committing new transactions. Instead, that's going to give them a ticket, a temporary share in a consensus group. So. And so what that means is, and so they, when somebody wins a proof of work, they get one of these, say, colored tokens. You could that's a special kind of block we call a key block. This is using a terminology that we adopted from Bitcoin NG, which also has a similar idea of decoupling that we build on, decoupling the mining-based blocks from the transaction commitment. So whenever a miner produces a new mining block or key block, it gets a temporary share or a right to be in the consensus group. And it still produces a mining blockchain just like Bitcoin. It's just that it doesn't have any transactions in it. And so at a given time, you can take the rightmost part, say 100 or the last 100 or the last 1,000 key blocks, the last number of sliding window worth of successfully mined blocks, and those all have public keys of representing the identities of the miners who successfully got those blocks, and those at any given time are the consensus group members that we're going to use for Bitcoin for our PBFT consensus process, right? So. Again, so there's a bunch of interesting details and potential trade-offs there, but that I don't really have time to get into, but I'm happy to discuss offline. But that's the gist of how we address the first mismatch between PBFT and Bitcoin. So here now to the second one: why we need PBFT to scale if we're going to use it this way. Why do we need it to scale? Why not just use a PBFT group of 4 or 10 or something like that? Well, the problem with that is when we build consensus groups this way, we want them to be statistically representative of the hash power, so that a miner or mining pool that has about 5% or 7% or whatever of the total hash power will consistently get about the corresponding 5 or 7% of the tickets in this consensus, of the nodes in this consensus group at any given time. And that only works statistically if the group is a non-trivial size. So 100 or 1,000 gives us pretty good assurance that the statistical distribution of tickets to mining power in this group is fairly close to the distribution of hash power in the overall network, right? So this is basically a sampling mechanism, and we need the group to be big enough for it to be a good sample, right? So we need PBFT to scale, but why doesn't it scale normally? Well, for a couple reasons. So I basically already mentioned that in summarizing how PBFT works. So the announcement or pre-prepare phase, where the leader announces what's going to be committed, is not a big problem. That's just one to many. But there are these two phases that are basically all-to-all communication. All of the nodes have to convince all of the other nodes that they're ready to go, and everybody has to add up all of the sign-offs from the other nodes. So these are not large communications, but they're critical, and everybody has to be convinced that, you know, a sufficient fraction of everybody else is signed off on moving to the next stage, right? And so, so if you try to scale this naively, the problem is you get an n-squared problem in both communication and computation and authentication effort, right? And so that's where we have to pull out new tricks and new and different tools. And so there's various ways to make this more scalable, but we use a tool we call collective signing. And this is not really a new cryptographic tool. In various forms, it's been around for a long time. But what we do is we take this this collective signing protocol that we built a scalable collective signing protocol before ByzCoin, and we used it basically to as a tool in this PBFT loop to make the all-to-all sign-off process in the prepare and commit phases much more efficient and scalable. And so I'll come back to how that works in a minute, but the gist is we organize the nodes into temporary trees, much like broadcast or multicast trees that are very effective at distributing video or things like that. But in this case, we're using these trees to broadcast efficiently broadcast announcements of the next phase, and also to collect sign-offs and compress them cryptographically into a single efficient signature, a small compact signature that basically is a compressed representation of a whole bunch of sign-offs compressed together, right? So I'll come back to that in just a minute, but the upshot is that when we do that, when we build our consensus groups this way, and we make PBFT scale using this collective signing optimization and other optimizations that I don't have time to talk about, we can basically run these consensus protocols one after the other as fast as each round can collect 2/3 worth of sign-off. It can move to the next round and commit more transactions. That means we never have to wait for 10 minutes or even a few seconds, a particular timeout, before we can go back and commit more transactions. And so that's how we get these couple of orders of magnitude higher throughput in our experiments. Even though we have hundreds or even thousands of nodes in the consensus group participating in this consensus, okay? And of course, the other big benefit we're getting from this is immediate finality. Once something comes committed, it stays committed, and that's just a property that comes from PBFT, okay? So, so let me look a little bit into the collective signing part of this. How does collective signing work? So like I mentioned, this is a protocol, another protocol that we had developed before ByzCoin, and it can be used for many purposes. We designed it for authorities like time servers or public key servers or update servers. But of course, in the last example, it can be used for sign-offs in a consensus process, right? And so some authority or leader, maybe just the leader of the temporary consensus group, is trying to get a bunch of witnesses to witness and sign off on a statement. And this uses, again, a very old, standard, well-established cryptographic algorithm called Schnorr signatures. And this is, there's a lot of interest in different kind of Schnorr signatures in the Bitcoin and cryptocurrency crowd currently, and for good reason, because it's a very flexible, efficient signing scheme for many purposes. But for our purposes, it has a very important property. You can compress multi-signatures. You can, so you can basically, so it's a 3-round cryptographic protocol where, in the normal operation, whoever is signing off has to create a cryptographic commitment. I won't get into the details. You use a hash function to produce a challenge based on that commitment, and then the signer has to produce a response. That's basically a zero-knowledge proof of knowledge of the private key that's entangled with the message being signed and stuff like that. But the important thing is that, say you have multiple signers, you want to have a signature representing the sign-offs of multiple group members together. Well, it has some very convenient mathematical properties that you can just have several signers produce commitments. You basically add them together in the appropriate group, produce one challenge from that using a hash function, and then have all of the signers produce different fragments of a response, add them together in the appropriate fashion, and basically they combine into what amounts to one snore signature that just has to be checked once against a common aggregate key, right? So again, I don't want to get into all the cryptographic details, and this isn't something new. This isn't something we invented. But the key is what we did is made this very scalable by creating this protocol that could do this aggregation over a dynamic tree structure to make it extremely scalable and to be able to collect and aggregate these sign-offs among thousands of nodes very quickly to make Byzantine consensus or other processes work well. Okay, so. Yeah, so I won't, I'll skip the details of the performance. Basically, the gist is it performs really well. Since I'm probably, what kind of time do you want me, how do you want me to adapt in terms of time? Okay, yeah. So I'll probably just barely summarize the OmniLedger part, but summarize some of the parts since I've been moving somewhat slowly. Okay, so we've talked about the basic structure of ByzCoin and the collective signing process that allows us to move quickly. I want to talk about some of the other things we can do with it to get related benefits. So one of the problems that any blockchain system has is when you have clients like the phones that you're all holding, and they want to verify that something is on the blockchain or they want to follow the blockchain. They need a way to catch up on the history, right? And of course. They can, fortunately, the Bitcoin structure allows them to just download the block headers instead of the entire contents of the blocks if you want to verify a transaction that might be old. But these devices, to securely verify that something is on the blockchain, any device still has to gossip with multiple parties. It has to make sure it can't be disconnected from the network. There's routing attacks and things like that, and it still costs bandwidth. And this led us to another idea that applies this collective signing idea. The fact that it leverages the fact that we're collectively signing each block that we commit anyway. It's it was kind of an accidental, synergy. We noticed, well, we're getting a collective signature on each block that we commit anyway. Can this be used for anything else? And it turns out. This is really potentially interesting for other purposes, namely for somebody else besides the group of nodes that's actually committing the blocks. Somebody else can check those signatures too, right? And so and this is useful to and so we because of this. we can create, so you're all familiar with the standard structure of a blockchain in which blocks are connected with hash links going backward. This allows anybody who knows the most recent block to verify the correctness or integrity of anything in history. Basically, it allows you to traverse from recent to less recent blocks from front to back securely, but it doesn't allow you to traverse the blockchain in the other way, right? To catch up from older to newer, you have to be gossiping or monitoring the consensus process. But with ByzCoin, what it's doing is it's producing collective signatures on these committed blocks all the time. And if we actually just keep those collective signatures, basically save them as additional parts of the blockchain, we create this intriguing structure that we're calling a skip chain, which is basically a bidirectional cryptographically verifiable blockchain, where a client, or a device or a mobile app who might not have seen the blockchain for a week or a month might be back here, and some other device might want to catch it up. And without having to gossip anybody, or maybe just gossiping with one device peer-to-peer, the out-of-date device can just look at these signatures, find them anywhere you can find them peer-to-peer, whatever, and catch up that way, right? So basically it creates new possibilities for actually following and verifying transactions on blockchains. So we extended this further. If you extend this further, using the skip list idea, we can create basically longer hops in both directions to make it possible for any device to convince any other device that some transaction of interest is on the blockchain wherever it is in history, either forward or backward in time, with respect to each other. So again, I won't get into more details. That's in a paper called Chainiac that we published in last year, IEEE Security and Privacy, I believe. And we applied it to in the application of peer-to-peer software updates. So you can have a lot of IoT devices, say, that need to be kept up to date. They can't necessarily be online all the time, gossiping block headers and stuff. Well, you can, if you put these software updates on this kind of blockchain, the devices can just peer-to-peer gossip the updates and prove to each other that, yeah, this is really a genuine update, and it's safe to accept it because it's signed off not just by one authority but by the whole collection of miners, right? So I think this is a potentially powerful and interesting abstraction for other purposes as well, such as certificates and other things. And so the point is, this is by taking this collective signing mechanism that basically comes out of the consensus process, we can get other useful, interesting functionality properties in addition to pure performance. Okay. Okay, and so I mentioned OmniLedger. So this is, on our continuing quest toward making blockchains more scalable. I'll only give you the bare gist of this as something to think about and maybe talk about in the future. So what scalability problem does ByzCoin not solve? Well, it leaves a lot of problems unsolved, but one of them is that even the ByzCoin blockchain still has all of the consensus group members and all of the validators basically verifying all transactions and doing all of the, replicating all of the work and checking that everybody is doing, right? And this fundamentally keeps blockchains is another reasons blockchains are having trouble scaling, because everybody is doing, is replicating all of the work, right? And that shouldn't be necessary strictly. And cloud computing, well, why is cloud computing so scalable? Well, because they break up the work and give this part of the work to one node and this part of work to the next node. And so in a cloud environment, when you add more resources, you get better throughput. In a blockchain environment, including ByzCoin, you add more nodes, you don't get better throughput. You maybe hopefully get better security, but you don't get better throughput. So the question is, how can we achieve cloud type horizontal scaling in a blockchain environment? And this is the problem OmniLedger addresses by building further on ByzCoin. It can use the same consensus group mechanisms, but it, instead of just creating one consensus group, the idea is it creates several consensus groups, each of them big enough to be secure and there's a bunch of details to deciding how big those groups have to be secure, but equally important, all of those groups also have to be good random samples of the total consensus group, of the total set of miners or potential consensus group members. And that's the other big challenge that OmniLedger addresses. And again, for lack of time, I don't want to get into those challenges in detail. But the upshot is that if you, by dealing with these challenges, by creating these smaller shards securely out of the big shards, and splitting work in the appropriate way between them, we can get further orders of magnitude worth of scalability out of these kinds of blockchains. And so in our experiments, we're already well into the Visa level throughputs, and the limits, the scalability limits we have here are related to the size of the test bed that we have, not the algorithms. So OmniLedger. So I mentioned it's critically important for security reasons for all of those shards to be randomly sampled groups from the total population, and it's critically important that nobody can mess with that randomness, even bias it, predict it or bias it. And so that relies on yet another critical tool that's needed both by OmniLedger and actually it's fairly commonly needed, I think, in many other blockchain environments. It's also a critical piece needed by most proof-of-stake systems, so it's a very common thing, and it's and I want to bring this up a little bit because it's such a simple sounding problem, but it's also so easy to get wrong. And there's a lot of people who try to build a distributed randomness protocol and get it wrong, and it turns out to be completely biasable. And actually this is another area where we have just continual evidence of wrong, biasable, or hackable, public randomness in various ways, going back at least to the Vietnam War. This was obviously pre-blockchain, but FIFA, speaking of the World Cup, FIFA got in trouble for bias, for crooked randomness, and there was an incident just a few weeks ago, et cetera, et cetera. Part of the reason it's hard is because you would think it's easy. So many of you are probably familiar with the idea of a cryptographic commit. If you want to mix up a bunch of randomness, how about just having everybody pick a random number and then commit to that random number, like take a hash of that, publish the hash, and then everybody reveal the random number to make sure you can't, and then combine those numbers together. So nobody could have seen anybody else's random number because you committed to it first, right? You would think that's secure, right? And a lot of people are actually doing it that way. Unfortunately, what people don't realize is there is an exponential bias attack when any non-trivial number of players in this environment are colluding, and you have to deal with the fact that somebody might refuse to commit, somebody might go offline, either either unintentionally or on purpose and just not reveal their share, you got to do something. You got to decide what to do without it. And you'll produce different randomness if they don't reveal their share. And the problem with that is if a node has, say, F, some number of colluding followers, they can stay online or go offline maliciously in 2 to the F combinations. If the attacker plays this game right, he can basically mine those 2 to the F combinations for the best of 2 to the F possible outcomes that's most beneficial to the attacker, and get basically an exponential advantage in whatever this randomness is used for. And that's a very fundamental principle here. And so as the systems gets bigger, the number of contributors to this randomness gets bigger, and the potential colluding group gets bigger, the bias vulnerability gets exponentially worse, right? And so this is why this kind of naive randomness protocol is so dangerous. That a lot of people are using. Now, I won't get, so, I'm already way out of time. I'm sorry for going over. I hope it's moderately worthwhile. I won't get into all the details of how to do it right. It starts with use Shamir secret sharing. This is a classic tool that's useful in this case as well as many others. You have to do it the right way. If you do it the right way, in the obvious way, it works, but it's not very scalable. So we get another scalability problem just in picking random numbers in a bias-resistant fashion, right? And so that's a focus of another piece of work we've done to figure out, well, how do we, for all kinds of reasons, we need scalable non-random numbers to scale blockchains. In other words, to get proof of stake, to get X, Y, and Z. And so, but there's actually a chicken and egg problem in this problem, because to scale even the randomness generation, we also need to do this sharding thing, pick groups, but how do we pick random groups when we don't have randomness, because we were trying to produce randomness, right? So there's a fundamental chicken and egg problem, and without getting into further details, these protocols do a careful dance, kind of a multi-stage bootstrapping mechanism to produce a somewhat scalable protocol that produces good randomness that's good enough to produce a really good, really scalable protocol. So. You can try out our beacon based on this. It's also used in OmniLedger and other things. So I think, I'll basically leave it at that. So I hope I've given you an overview of some tools. So we're a research group. All of this is implemented in open source code. It's not really deployment ready in most cases, but you can download it off GitHub, and you can play with it. I wanted to say more about future work, but I will skip that for now. And just conclude. So, of course, we're, as a research group, we want to get these ideas deployed in whatever form. We're happy to work with people interested in doing that. We're already working with quite a few startups and other companies, some of whom are supporting our research. Many other companies have been taking our ideas and just implementing them in different emerging protocols. That's great too. They're all open source. We like when people steal our ideas, so you're welcome to. Here's the links to the most important GitHub repositories where all of the code lives, and you can find all the relevant papers on our website. And so I hope this is a useful and interesting snapshot on some of the relevant tools that I think will be very useful to build more scalable blockchains. So thanks a lot.
Thank you very much, Bryan. Are there any questions? No. Hang on. Hang on. We have a second one.
I'm more interested in like the computing slides.
Okay. Yeah.
In the end now, but I'm not sure like how everybody.
Yeah. So
time now.
yeah, if you want, you know, if there if there's enough interest, yeah. So this was where I want to kind of gaze into the future and kind of figure out, well, what tools are we still missing? Which is also an important question. We're not to nirvana yet, obviously. So where next with blockchain scaling? Of course, this can go in many ways, but I think one of the most important ways and useful ways is to recognize that we need, just like processors have gradually decomposed into different kinds of special function units and kind of a Cambrian explosion, say, of special function units, not just within processors like ALUs and instruction units and stuff, but whole different types of cores like GPUs and tensor processing unit, different specialized functions. I'm predicting, and I think it's both useful and practically unavoidable, that we're going to see this kind of thing happening in blockchains and decentralized systems, where we're going to start to see not just homogeneous. So in OmniLedger, I talked about these homogeneous shards that do just different shares of the same kind of work. I think we're also going to see heterogeneous shards, different types of functions, or shards specialized to different types of functions, such as computation, the kinds of things that Ethereum does in the Ethereum virtual machine. Private computation, things that computation using multi-party computation or fully homomorphic encryption or other things like that. Function units for specific things like, say, choosing random numbers in a strong, unbiasable way, or shuffling things, or things like that. So I think one way or another we're going to, and we have to see this ecosystem of functions becoming more heterogeneous and more modular, because we can't keep doing complete forklift upgrades and hard forks of blockchains every time we add one little upgrade or function, right? And so we got to figure out how to upgrade blockchains and add functions to blockchains in more modular fashion. And I think this kind of sharding brought to a heterogeneous level is one way to do that. And so we have some work, for example, addressing the privacy problem, making it possible to store secrets in a blockchain and trust secrets to a blockchain. This is in a preprint called Scarab, hidden in plain sight, if you're interested. That's just kind of one type of potential interesting special function shard that we envision. So I won't get into that. Other ways you might want to create shards are based on locality for performance, so that you can have a Berlin shard that the speed of light is not that far across Berlin, so you can have that shard operate really quickly. But of course that creates both security and technical challenges to manage all those locality shards. So yeah, I know I'm way past out of time, but I hope that satisfied some of your interest in that kind of future speculation. So this is all future speculation and stuff that we're working on. Others are working on some of that too, but yeah.
I think we have 5 more minutes for the questions, because they're usually very important.
Yeah. Hi, I'm Yuri. A very short question. Could you tell a little bit for cost side of your solutions? To the cost side?
Cozy, the collective signing.
Yeah.
What do you want me to say about? You want me to say more about Cozy?
No. Cost.
Oh, cost. Like financial cost.
Yes.
Good question. As you might notice in the ByzCoin architecture, one of the things that we didn't change was the dependence on proof of work, right? And so from that perspective, if you're building And all of the additional scalability aspects that we're introducing still basically build on that in the most natural, obvious form. So if you keep that, then you basically inherit the same incentive and reward structure as Bitcoin. Now, I don't think that's necessarily the right way to go. And another very interesting and important topic is how to replace proof of work with something better. I mentioned proof of stake as one alternate approach that a lot of people are, I think, rightly interested in to reduce energy use and at least energy cost. From that perspective, and I think that's super important. So we need to get proof of stake, deployed as quickly as possible. This wasn't a proof of stake talk. I could do a proof of stake talk too, but and I think we definitely, at least in the research world, we have all the tools we need to do secure proof of stake. We just need to get them deployed, and stop wasting this huge amount of energy. At the same thing, I don't think that's the final goal either, because proof of stake is still going to have the recentralization problems that proof of work does, and other things like that. And so in another talk, another interesting concept I'm happy to talk about is an alternative that we're developing called proof of personhood, which is the idea, trying to decentralize in a one person, one vote sense, where every real person gets 1 unit of mining power, and there's a lot of, if we could implement that, then there's a lot of interesting stuff we can do with that. But of course, that's not trivial. So is that addressing your question, at least in terms of the mining costs and stuff like that? So this does not address that, but it's also a very important thing to address elsewhere.
Yeah, hi, thanks a lot for the talk. You did a lot of stuff. Crazy. I actually have 2 questions, but maybe I'll just start with a maybe more interesting one. You evaluated your ByzCoin specifically, as far as I understood, without any attackers, right? So how is your optimization working if some nodes are just spamming Cozy, for example? Or
Right. So we have evaluated with churn and unreliability. So we did not try to do extensive, intelligent, malicious adversary like red team testing. And so that's an important aspect of testing and development that still needs to be done to make it fully deployable in the real world. There are, in terms of Cozy, we have identified some potential denial of service attacks that risks that actually the paper goes into in a fair amount of detail. One is, well, what if a denial of service attacker forces some number of nodes offline, especially at a bad time, and forces the leader to recompute the trees. Now, kind of the leader can recompute the trees anytime, but how does he decide when to do that, and what happens if the leader is malicious too, and the leader is trying to maliciously censor nodes who are online and pretend that they're offline, right? So we do explore some of those kinds of attacks in the paper, but and in the context of PBFT, in principle, they shouldn't be serious problems, because anytime the leader or the consensus group stops making progress, what's supposed to happen is that all of the other nodes get impatient and cause a view change, the standard PBFT thing. And then some other leader is elected until eventually you get to a leader that's not malicious and that makes progress. Now, that's the theory. That's how it's supposed to work, But that's one of the areas that's really incredibly difficult to get right in practical PBFT-based protocols. And so any given implementation absolutely has to be analyzed like crazy and red team tested like crazy before I think we can get real high confidence that it's immune to those, many of those kinds of DOS attacks especially, and things like that. So, okay.
All right.
Yeah.
Any other questions? If not, we can continue the conversation with a cool drink. Thank you.
As a consequence of using PBFT, is it fair to say that the threshold of tolerance towards malicious actors in the system is lowered from 1 second plus 1% to 1/3 plus 1%?
Very good question. Comparing the threshold, the relevant thresholds between Bitcoin and a PBFT-based protocol is actually quite problematic and subtle. So Bitcoin was, intended to be, tolerant to, 49% attacks. It turns out it isn't because of things like selfish mining, that actually, vulnerabilities to some types of attacks, especially including selfish mining, kick in at around 33%. They don't make a catastrophically fail immediately, but they start causing serious problems. Depending on the way you look at Bitcoin, its tolerance threshold is somewhere between 33 and 50% as well. And then if you look closely at PBFT algorithms, you'll notice that the reason for the 3f+1 formal requirement is the reason that's 3f+1 is based on a very, very strong threat model that assumes that whoever the attacker is, they have complete control over the network, and that they can completely, the attacker can not only control a threshold of F, up to 1/3 of the nodes, but also can completely control which of the honest nodes can communicate with which of the other honest nodes when, right? So if you just slightly weaken, and Bitcoin doesn't really operate well in that kind of super strong threat model where the attacker completely controls the network either. If an attacker can split the network, they can do really bad things to Bitcoin. That's well established. There's other great research about that, and BGP attacks against Bitcoin and stuff like that. And if you slightly weaken the threat model and into a synchronous model where you assume that the attacker can't prevent the honest nodes from eventually at some reasonable time being able to communicate with each other, then you can actually, PBFT can actually go back to 2f+1, right? So, under the right conditions, and that's some of the right conditions. There are other ways that condition can be met. So again, depending on the subtleties, PBFT algorithms also tend to go somewhere between 33% and 50% tolerance, but the subtleties are different from the subtleties that apply to Nakamoto consensus. So it's an interesting question with no very simple answer.
Good. Bryan, I think you gave us a lot of ideas and inspired us, and we have a lot of reading to do now.
Sorry.
Thank you all for being here tonight. See you again next time, and get a drink at the bar.